So today my presentation will be on leveraging linked data and ontologies to enhance generative AI. And I would first start with a definition of we are hearing today generative AI and large language models and how this fit in the world of the big world of artificial intelligence. And here we have to understand that large language models are artificial intelligence models that have been trained on large amount of data using a particular deep learning architecture, so these transformers. Um, and so they fit in one of the, and in one part of deep learning methods. And large language models are also partly generative AI. So generative AI is models that are able to generate new data that are similar to what they already seen and understood. And large language model is a particular also model in this way. So the capabilities of large language models is their ability to generate coherent text. I would not say true or not, but it's at least coherent, to answer question, to understand context, to which make them a versatile tool in text, image, hypothesis, questioning generation. They can be used in chatbot, they can be used to generate content, to translate text, or even to translate code, to assist in research and different steps of research. And one of the major limitations we notice is also these models can produce biases and can produce incorrect informations, which would name as hallucination. And a second definition also in now in this session, so we'll be talking about ontology and semantics. And I would start with this this part of the screen where it's about this what we call 5-star data scoring. It's how it's ranking the data on their openness and their availability. And so the first star is just to make things available on the web. The second star is to make things available in a structured way, Excel table instead of just scanned image of a text would be better. Making things available in an open format. Use URI to connect things and that people can point to what we are sharing. And the 5-star thing is to have linked data that are providing the concept and that are open linked data available. And when we talk about knowledge graph, I would say a simple example here. So for example, if we have a data table and in one of the columns cases, we read Albert Einstein. Actually, our brain, in a way, understands automatically that Albert Einstein is not only a string of characters. It has meaning, it has a context. So Albert Einstein was studying in University of Zurich. He was studying in ETH Zurich. He got an academic degree in Zurich, an academic major in physics in Zurich. And these connections that our brain is doing, we can also bring them to the knowledge we have in databases. And this is where these knowledge graphs are interesting because they are creating connections between concepts. How concepts are connected together, what is the link between the different concepts we see in our data and we could see also outside of our data. Now, when we try to connect knowledge graphs and large language model, we see that each of them has pro and con. So for example, large language models can generate knowledge, can process language, and can be generalizable. On the other hand, they have implicit knowledge that is complicated to translate or to explain from where it's coming with is what is the typical knowledge that produced this answer the model gave us. They are subject to hallucination. They can be indecisive. They are a black box they were trained, we know how it worked, but we don't know how they reason to reach the answer. And they are also generalized, so they are also lacking domain-specific knowledge that could be interesting in some questions. On the other hand, knowledge graph can be incomplete, can lack this knowledge understanding ability, don't see unseen facts, and is not able to integrate them there. But knowledge graphs offer structured knowledge, offer more accuracy, can be more decisive, are interpretable, so we can know from where the information is coming, can support the interpretation. Often they are domain specific, so the ontology that is linked to this knowledge graph is defining a specific domain, and also it's a knowledge that is evolving compared to one version, for example, of a model that is trained on a set of data and then it's set this way, it's available as a foundation model this way. Knowledge graphs can be evolving when the ontology continue also to evolve. And the thing is, combining knowledge graph and AI can be interesting in both senses. So what knowledge graph, how knowledge graph can be applied in generative AI is, for example, to train model, validate these models, to AI can process natural language that are available in knowledge graph. They can offer recommendation systems knowing this knowledge, but also knowledge graph can support reducing the hallucination of these models. And I will start with this part first, on how could hallucination be reduced using knowledge graph. And I don't know if you perhaps heard about RAG, which is retrieval augmented generation. So how this work is when a user give a question to a large language model. So the classical way is the model will look in what he was trained on and generate an answer. But there is also a way to augment this answer by giving the model access to external language, to other language that was not used to train the model. And here the idea is to have in the middle a retrieval model that will look in a knowledge database and could retrieve relevant information that are connected to the question the user is asking, combine the question and the augmented knowledge to generate a better answer, a more contextual, a more enhanced answer. And this improves a lot the effectiveness of the large language models. But just imagine if now, instead of only extracting unstructured information, the retrieval model looks in a knowledge database and that is graph database, and extract relevant information in a knowledge graph structure that not only brings the knowledge, but also brings more context to the question we are asking and to the knowledge that the model will be using to answer the question. And on the other side, also, generative AI can have some applications in the knowledge graph world in a way of supporting and enhancing the construction of knowledge graph, of integrating data, and enriching it, and enhancing research or retrieval of information. And here in this part, I will look at this step now of the connection between knowledge graph and generative AI. And let's first introduce how, let's say we have legacy data that is in an Excel file, unstructured, not really clean. And then how could we convert our classical data into linked data? And if we start with our data, then we need to extract the concepts and the relationships that are in our Excel table, for example, to identify what are the appropriate or relevant ontologies that are usable for our concepts and our relationships, then to map the concepts and the relationships with the different ontologies that we identified to establish these connections, and then to make the data connected, available, open to external. And this steps of the link data or graph database even creation is not really straightforward task. So it's always going way and back to adopt things, to correct things when we are creating this linked data. Finding ontologies that also match the context of data can be really a tricky task. And it's also usually time consuming and very labor intensive. This also what is refraining people from converting all data that they have. And also what we can also talk about is it's also needing ontology specific knowledge. So it should also, it's not an IT task. It should be done with people that are in the field, knowing the ontology they are talking about, that is usable in their domain. And for this, to support the conversion of data, what we developed is tool that allow user to support the users in this steps that need a lot of time and efforts to accelerate the process of converting data into linked data through two different applications that are large language model based. So one application is I would call it an ontology recommender. So to recommend appropriate ontologies that can be used then for mapping the concepts to the ontologies. And the extraction app is an app that knowing the ontology and knowing the knowledge we are talking about then is able to create triples and different file formats with extracted entities and with connected entities also. And all this is also able to use plain text because of the ability of the large language models to extract also concepts from a plain text. We keep also here the human in the loop meaning that it's not fully automated and the human can guide also where the model is going by defining and modifying the prompts that are used. So first for the ontology recommender, so for example, just imagine from plain text, a report or a scientific paper that is feed there, then it's predefined prompts for selecting the ontology. So the prompts are already there, it's standardized. And there are three ways of using the tool, I would say. So just simple prompt to ChatGPT. It's ChatGPT based here. We can think of open source models also that can be used locally if you don't want to share our data at this step. With this prompt, to have then the best references, the best ontologies also per concept, and to recommend ontology for the full dataset coverage that we are talking about. Then once we have an ontology that is checked by human, that is validated, then we can send it to the second tool that will extract data from plain text. So there are different options for either only doing the named entity recognition or creating also the compound class. Also, again, giving the text and giving the YAML file, so with the simplified schema of the ontology, then the model is able to extract the entities, to link them to the ontology, and to provide at the end different JSON files with named entity, with the compound classes, with the named entity and their compound class combined, and in a RDF format with this triplet setting. There's also the option here to use different models. If you can see it here, it's not really clear, but should be clear in the PowerPoint. It's different models for the different steps that the model will be, the tool will be doing here, from the named entity extraction, the class extraction, the formatting of the files. For all these steps, it's possible to calibrate own models. For example, which model, in my opinion, perform better for my domain-specific knowledge there. Also to support the conversion of data into linked data in the context of KIDA project. So KIDA project is a German project founded by the Ministry of Agriculture that is connecting different institutes under the Ministry of Agriculture in Germany for accelerating artificial intelligence and data. And here we have developed a service offer to support the conversion of data into linked data by offering consultancy, so advices on the generation and how to use linked data, advices on projects that want to implement linked data, and having and matching their data with the FAIR principle, being findable, accessible, interoperable, and reusable. Also to support the generation of linked data, so support the conversion of data into linked data and have some topic-specific mapping to ontology that match the data. And also something else that is under development is to provide data, linked data repository in this project to explore the data and to make it more available. And actually, my presentation is a bit to loop that AI needs to have more structured data to produce better results. AI can also support creating better structured data, and it's some kind of a positive loop that better data would allow to have better model that could produce better data, and we can really improve a lot there. And if you go one step back also from artificial intelligence, providing data into structured and interoperable data is very important to improve the interoperability of data, that we can make them machine readable also for other tools we are using. To also to develop such tools and such services or such advice to how can we convert data into linked data is needed to make people adopt these formats and to make people convert their data to take more advantage of what is already available out there. Most of the time we have a lot of data that are either between countries, even between in the same ministry, between different services. Everyone codes the data the way he thinks it's the best for him, and it's often very complicated then to reconnect things together and to compare things after that. And here also to to go back now to our AI discussion, as said, this can be AI assisted, but it's very important if you want to avoid this hallucination problems to give the appropriate context and to give the appropriate knowledge specific to the AI models to make them produce better results. And thank you for your attention and welcome to your questions.
Thank you very much, Rasim. It's very interesting presentation. And the floor is open to any question from the audience, please. Hello. I ask to help because the camera, because we have the third presenter online, and present yourself, please. Thank you very much.
Hi, I'm Scott McClure with DTU in Denmark. A lot of what I do is that box that you drew. So I guess one short question and one longer. The short, those links, is that proprietary or is that open?
So if we can go, now we tested it with two open source ontologies yeah, because in there also you have this ontology retrieval part. I have to remember the names, but it was open for now at least. But it's also possible, as I said, it can be hosted locally. You can use your own ontology. You can introduce your own knowledge in the large language model. This also what make it very versatile, that you can use your own knowledge integrated to the large language models that are doing these different steps to make them more specific for your use case.
But I guess, is that available online? So I saw your links are.
It's online. It's entering a development phase to be in production, entering the production phase. For now, it's available online, but you need to be granted access to it. And you have access, as I say, to only this proof of concept, the idea, what to see if it's possible to make this work faster, because sometimes it's taking months to convert even a not too complicated database into a linked data structure.
Yeah. And then just, have you done this with any of the LLMs that are completely local for sort of like GDPR data kind of?
Yeah, we had we used so we used at this time it was GPT-4 Turbo and GPT family. We used the Llama 3, yeah, and some others. So we compared both solutions because we think also the data privacy problem would in some of the requests we are having is also problematic, that sometimes data cannot be shared with ChatGPT, and then we have the option to use a local version of Llama, for example, to produce these outputs.
Thank you.
Very good.
We have more questions. Yes, please.
Thank you. I'm actually Paul Duvalier with EFSA. Actually, I'm trying to formulate the question. Maybe you can help me. We've seen applications of AI which find correlations without ontologies. I think we've seen a few. In this human in the loop process, the speed with which we are defining ontologies and using them to improve LLMs is at the pace, the speed of human work, as opposed to the growth in all of the, what did we call it yesterday, the untrusted but this unusual data, which is growing at an exponential rate. Are there other techniques that you have seen that don't rely on ontologies that can help improve LLM and reduce hallucination? Are there alternatives?
I would say if we come back to here, it's already what this 5-star think is a bit about. Still, what this linked data story brings to the large language models is also the larger context that the ontology bring with it, that is not available in the raw data, if I would call it this way. But anyway, making data even connected to concepts is already good. Even if we don't reach the point of having graph data, even if we don't reach the point of having linked data format, having it structured is already good. By, as you said, creating only connections, even if they are not standardized, could bring something more to AI, something that is not seen in the raw data. what the tools are using, they are not creating the ontology. They are only connecting with existing ontology. And this is the speed gain we have, that instead of pointing the on the concepts that are in a database or in text with ontologies and then seeing the connection and then selecting what ontology we are talking about, because something can be defined in many different ontologies in different use cases that are not perhaps fully the same. And this what the tool accelerate, this ability to identify what is the ontology to use to connect the concepts that are in my text or in my data, and creating the connection afterwards. But it's not really creating ontology from scratch. It's even going and looking for publicly available ontologies or ontology research to bring the appropriate ontologies and to compare what ontology should be used when I want to link my data.
Okay. Please.
Yeah. I will introduce myself. Yeah, so Vikas Kumar, also from the BFR, but currently we are not linked, and we are trying to be linked in the different department. Okay, I'm also doing some of this work, but in another European project in the park. I'm coming to your question of this, the hallucination and the ontology. Hallucination, the problem of the hallucination is not just the ontology. You know, the ontology is just the one part of interpreting the knowledge that we have in the text, right? But regenerative part of the model, which is what creating that. So my question is here is that, which is again coming to for the discussion for the whole community, is that the problem that we are trying to solve here is the extraction of the knowledge or extraction of the information from the unstructured data. And we are trying to use a regenerative model. Why? You know, extraction is a simple problem of linking the entity and then relationship between the entity and then extracting that information in a structured form, right? Why we want to attack this problem with a regenerative model? What is giving us? Why we want to do that? And this is where is the fundamental mistake that we are doing. We are all trying to generalize a NLP problem, natural language processing problem, through a model which was not meant to be doing the knowledge extraction. They did the knowledge extraction behind it. They interpreted for themselves, they trained themselves, and now they are regenerating that knowledge, you know. And with that, then we are trying to extract the knowledge. And this is fundamentally what we are doing, is that we are doing it wrong. And this is where I want to come, you know. So the whole discussion that I have seen from the study, this is all the large language model which has been built for a general purpose that we are all using, and we are all going gaga over that, you know. And this is where I'm getting it, like, you know, confused that what we are trying to do here.
I would say to complete a bit there also, that what the large language models are offering is this ability to be used in different domains. Tools we are talking about on the other side of creating usually ontology are domain specific. The schema of how to define things is very domain specific, while this offer a bit more flexibility. Another point also that I didn't mention, the ability also to don't use the out of the box, for example, ChatGPT. You can have long chain and add other knowledge to the model you are using to extract the entities. I would say something else also I didn't present here is the evaluation of these tools. We did the evaluation, and as you say, the models are very good at identifying, so in the named entity recognition task, they are performing a bit worse in the creating the connections and connecting stuff, but also because they are lacking this ability to make this connection, and this where having data that are already connected would enrich their ability to do so. Another point also perhaps that is very important when we are developing such tools, what we face is the lack of validation data is always the problem because we tested we when it went to evaluating the performance of these tools compared to other stuff, then we figure out that even what is called true, the ground truth, is not really the truth. So it's also sometimes the large language model was identifying mistakes in the human work of linking things and way and back. It's this way, but meaning that also it's not really the truth, and then we need to generate such data, such good data to be able to set to know where we are going and how to improve also these performances. Perhaps one last point, if I can say it also, that in
Yes, the
BFR we
last
are
point.
organizing a linked data symposium in December, and you are welcome to attend there and to see the discussions. So it should be on the 12th and the 13th of December, and it's in the context of this KIDA project.
Thank you, Rassam, for your nice presentation and for the invitation for the workshop. And now I would like to present our next presenter, Milan Yanosov, a data scientist, has a background in physics, a PhD in network and data science, and a current focus on geospatial data science. Milan is a startup co-founder. He is listed on Forbes 30 under 30 entrepreneur and a public educator and classified as a top voice in LinkedIn. He is author of the #1 Amazon bestseller Geospatial Data Science Essentials. And we are very exciting for listen your presentation, understanding the food home via network science. Please, Milan, the floor is yours. Thank you very much.
Thank you, and hi everyone. So my name is Milan, and my background is actually in physics, and later on I became a data scientist. So I'm really, really far from food science. So I thought that I will put together a more introductory talk for today, where I'm going to show you how network science can be used in analyzing food data, and also say a few words about our project with a really cool team, also including Akos, where we started to use network science and graph analytics to understand how the main types of foods Hungarian people consume may lead to various health concerns we are experiencing in the country. So, just to start this talk with a little bit of intro and overview about networks, I want to say a few words about how network science came to life and how flexible and how wonderfully adaptable network science is as a framework. So it goes back to a very distant topic, both in time and also in terms of the field of study, because the first graphs were born thanks to an urban planning or transportation dilemma. Back in the day, in the 17th, 18th century, there was a puzzle in the city of Königsberg saying that there is no way that people could walk around the 7 bridges of the city in a way that they only cross every bridge just once. Sounds like a very, well, impractical problem, but at the end it had a very huge impact on science because thanks to one of the leading mathematicians of the time, Leonhard Euler, this problem was leading to the birth of graph theory. So a graph, which looks like this one here, is in general a very simple object. It has nodes, these points, which are connected by lines or links or edges. So graph theory as a mathematical field is studying various rules about these graphs, but for them these are really just points connected in certain ways in certain patterns. At least for me and data folks, the real fun comes when we start to fill up these networks, these backbone structures with data. And this data can be coming from any field, literally. These nodes can be people who are related if they are, for instance, working together, if they are following each other on social media. But these nodes can also be, for instance, cities which are connected by railway or air transportation. These nodes can be countries which can be connected based on, for instance, how much they trade in terms of different commodities. And also, these nodes and links can be turned to biology in numerous ways, from, for instance, food chains, so which animal species are eating which other species, to gene regulatory networks, or even food items and their chemical composition. I have a few examples which are kind of showing in a more colorful way, especially if we can switch these lights off a little bit. So these few examples show how visually interesting and also meaningful network graphs and network representations can be. Here, if you see some of the nodes, which I'm not 100% sure, you may see the social graph of the Game of Thrones series, which on the one hand shows that we can turn literally anything into a network. So it's absolutely a very generic framework. Here, every node is one character of the show and they are linked if they shared any scenes in the movie. And the way we can interpret such a network is that, for instance, we can start picking the most central nodes, figuring out who are the major hubs in the network, let it be a storyline or a genetic or gene-protein interaction map. We can also map out the different clusters of nodes. For instance, in this case, they usually correspond to the different storylines, but network clusters can have loads of other meanings depending on the topic. So just to see how far these topics can go, this network shows a close-up of the most famous soccer players from the previous FIFA World Cup. Here again, we use the very same network methodology to map out which soccer players from the national teams were playing together in which clubs and how much time they spent together as teammates. But we can map other things besides people, as I just mentioned before. For instance, brain is a very good example of that, especially that it's also a biological network. Yes, so here in this project, I was helping a group of ethologists and veterinarians where they were conducting fMRI scans on dogs, and they were interested in how to turn these fMRI images into maps, network graphs, which were mapping out the functional connections between the different brain regions of dogs. And with this topic, we finally arrived to the food part, and this network is probably one of the earliest graphs of food science or earliest networks of food science. It is coming from one of our collaborators in this project and also my former mentor, Albert Laszlo Barabáshi's group. And they published this network more than 10 years ago, and they called it the flavor network. In this project, they were analyzing two datasets. One of them was a simple food and flavor molecule database. So they had information on which food items do contain which types of chemical molecules, which types of flavor molecules to be more precise. And they also had a large database of recipes, so just the instructions on how to cook certain types of foods. In this network, you can see that, hopefully you can see that the nodes correspond to different food items. For instance, here there is olive oil, here there's vegetable oil, there is onion, garlic, egg, for instance. And the colors correspond to the different food categories. For instance, this yellowish color here corresponds to fruits. Here we have alcoholic beverages, here we have meats, here we have vegetables. And two food items here are connected if they are sharing any chemicals related to their flavors. And the more chemicals they share, the stronger the connection, which leads to a kind of obvious clustering that similar food items like dairy and meat are clustered together. So here the map, on the one hand, seems trivial that, okay, meat is clustered together. On the other hand, and here one of my favorite book titles ever says that everything is obvious once you know the answer. And these maps are very similar to that. So once we see it, it seems intuitive and we can start reading it. However, drawing up a network map like this, just by looking at the different food items, would probably be very challenging for a human. So that's the first part of the study when they mapped out this flavor network, which is already very interesting on its own. And the first question they asked is how can they relate this to recipes and different cuisines? And turned out that in their comparison writing, they compared American and Korean cuisine, but the main idea was to compare Western and Eastern cuisine. Turned out that the network can explain very well how these two different cuisines work, because in the American and the Western version, cuisines and dishes tend to combine very similar food items. So the closer they are in the network, the more likely they will be combined in a dish. Just like think of hamburger and all the salty stuff that goes into a nice American hamburger. While on the other hand, Asian food tends to combine food items which are as far as possible. So the further two food items are on this graph, the more likely you will find those items in an Asian recipe. For instance, just think of sweet pork, which for Hungarian is a pretty odd thing, but all my Asian friends love it, and I'm also learning to enjoy that, but that's probably a different story. So this is already a nice early example of how networks can be used in food science. And now a few words about the pilot project that we have been working on. So this network already showed that there is a pretty complex ecosystem of food items, but that's just half of the story. The other half is that what happens once we consume these food items, and then what happens in our body, especially on the long term. So what possible health effects could these food items and all the chemicals inside them have? And here, I'd like to make a poll because at least for me as an outsider for food science, this was very shocking to learn when I started working on this project. So how many molecules do you think, different types of molecules, are in an apple? If you think it's around 100, please raise your hand. About 1,000? Uh-huh. About 10,000? Okay, so that's good, thank you. So it has a very uniform distribution. So we will see where these slides go. So in the pilot study, we decided to map out 8 different types of food items in a very great details. So this is a pilot, that's why we had this relatively narrow scope, but the methodology is quite easily scalable if we have the right resources. And the 8 key food items for the Hungarian diet were pork meat, potato, onion, tomato, apple, and palinka, which is the local version of this really strong liquor made of fermented fruits, usually around 40-50%, so it's certainly part of a healthy diet. And we wanted to profile these food items from various perspectives. I will later show all the databases we used. The main idea was to collect information on the chemical composition, so what types of chemicals have been identified experimentally in these food items, what kind of chemicals are have been inferred to be there, and if there is some information, then what is the quantity that's there. Of course, and there is already a spoiler. This is a figure from before the project. Here we already have 7,500 chemicals in just a single apple. That was, for me as a non-food scientist, really shocking that it's just a single apple. And even if there is like microgram concentrations, if we just think of the usual medications with milligram concentrations, that can be pretty concerning on what kind of stuff we are taking in when just having an apple, and not to mention all these ultra-processed things these days. So the goal here was to profile these food items, build a general data profile that has various fields, various information, including chemical composition, including different varieties, including possible health effects and disease associations, and a few other dimensions that will later on be mapped on an actual knowledge graph. And why do we want to map this on a knowledge graph? So the previous network with the flavors and the food items show you how different types of food items are related to each other. And here, coming from a review paper from this year from the Barabashi lab, I'm bringing an example where this knowledge graph or network shows how different chemicals found in food are linked to different cardiovascular diseases. For these yellow squares correspond to the different types of diseases. For instance, there's total stroke and hypertension. And the smaller nodes around them are the chemicals from fibers to proteins. And whether a link between a disease and the chemical is blue or red, it means whether it's a harmful connection, so that kind of chemical and the intake of that can cause these illnesses, while the blue connections mean that they have a supportive or preventive effect. For instance, here we have peripheral artery disease, and here we have a few chemicals. Um, I'm not sure I can spell out the names from this way, but these guys here, they are causing this disease, while the blue one here is actually healing it. So if we would like to avoid having that disease, then we should tailor the diet in a way that it contains only those chemicals which are connecting to a certain disease using the blue or connected by the blue edges. So having such a map, of course covering all possible diseases and food items mapped out, should be a great way to quantitatively engineer perfect diets. And for that, we need loads of data and very high quality data. And in that domain, we have a lot of work to do. So the first database in this project we merged, I think we had 6 or 7 databases, is already kind of a unified database coming from a few years back from the Warabashu lab. They call it the Nutritional Dark Matter Database, which is a relatively large dataset containing food items and their chemical composition, including the food items' English common names and scientific name, including the constituent chemicals in various naming and notation formats. However, this database is far from being complete, and there are also data cleanness issues and incompatibility issues. So this database alone doesn't solve the problem, but it serves as a very good foundational layer, which we started to extend with a few other databases. For instance, we added a very specific dataset about flavor molecules, the flavor DB, which means that in terms of the flavor dimension, our chemical profiles are much more detailed. Of course, this is a narrow segment of the full profile, but it's also a great addition. And then we added, for instance, the USDA food database, which contains food items and food products. So it doesn't only contain raw food items like pork meat, but also a bunch of processed versions, which is on the one hand, of course, very important because we are consuming these processed versions like grilled and cooked and boiled and in any other ways prepared pork meat, for instance. But it also shows how complex this problem is, because it's one thing to have a set of chemicals in the raw materials, and it's another thing what happens when we process it and prepare it in our kitchen. So now we are at the stage of trying to understand and map out what's at least in the raw materials, and then we will be able to move on to figure out what's in the final product that we are consuming. There are a few more databases. Probably the interesting one here is the CTD, the Comparative Toxigenomics Database, which contains chemical, disease, and health effect associations. So it shows us that different chemicals can relate to or can cause or prevent different types of health effects. So here we have a bunch of information that connect food items to chemicals and chemicals to health effects, which are really great information to turn into a knowledge graph. So now I'm speeding up a little bit because these are just technical details. For instance, in the final part, we had more than 9,000 chemicals linked to apples, and 200 of them were manually added in a pretty large manual data extraction and literature review effort. So even in this pilot project, the team was able to identify like almost 200 new molecules that were not identified before, but they are still there in just even a simple apple. And this was a great start to build a knowledge graph. So knowledge graphs, we have already seen them, but as a network scientist, I think that knowledge graph is more like a fancy term for a specific type of network. So knowledge graphs are networks where we have different types of nodes, not only food items, for instance, but food items, chemicals, health outcomes, diseases, and so on. And they are connected in various different ways. For instance, food item can be linked to a chemical when it contains the chemical. Chemical can be connected to, for instance, a concentration level, because ideally we can measure that In practice, just a few percentage of the chemicals have measured concentration levels, by the way, so there's a lot of work to do in that domain. And again, food items can, for instance, have flavors, and flavors can have corresponding molecules, and these molecules, again, can have concentrations. And these are all the types of relationships that we can map in a knowledge graph. So in terms of the technical details, at this point, once we combined all the databases, we started to figure out which types of nodes would be appropriate to use in this knowledge graph. And probably I won't read this out, but yes, see, you're taking pictures, so yeah, that's probably a good way of consuming this slide. So here listed all the types of nodes that we have: food items, chemicals, flavors, concentrations, and a number of other things, even information on where these results, for instance, measurements, are coming from in terms of the publications. And then we also defined, and also time for pictures, the different types of relationships between all these nodes or all these entities. And they are the best visualized on this simple network, which shows this ontology in a graph format. So this is kind of the blueprint of our project on how we organized all these food items and all their properties into this knowledge graph. So this is the blueprint which we use to build the network. Yes, feel free to take the photos. I will wait for everyone with that. Maybe we will also share the slides afterwards. Yes, we will. And the network we arrived at, based on 8 food items, had more than 30,000 nodes and more than 100,000 links. And these are just 8 raw food items. So if we just look into our fridge, well, we will see a lot more stuff than that. And then these are all various links, connections, and a bunch of health effects we today have no idea about. And to close this presentation, I wanted to show you how the final knowledge graph looks like. So this nice piece of art is actually the knowledge graph containing about 10, 15 types of different node entities, about 20 different types or 30 different types of relations between them, and the 100,000 connections between all the elements. So that's it for today, and I'm also thankful for the team I got to work with here, because this was a large collaborative effort. Also, special thanks to Ákos for inviting me here today. And if you would like to read more about networks, also the promotion part, my next book is coming out in about 3 weeks. So here, if you want to read more about networks, then this would be the right place. So thank you very much for your time. And questions, right?
Yes, I don't know if from the audience we have any questions. Eva, please.
Okay, Eva Scharfenberg, I'm just a data manager. I'm not in science anymore, but I'm a nutritionist. I have a question for you. Your visualization was very nice, beautiful, and challenging. And I have to say that I would never not eat an apple because one of those ingredients might have any effect on any disease that is on the earth. So how can you reduce? I mean, that's not a science question. It's more like a practical question. How can you reduce information in these dot graphs just to see what per food item might be the relevant to have a practical use of it? Oh, that's the question. To have a practical use of it, to reduce
Yes.
the dust. I mean,
Yes.
which is very beautiful. So that's the question.
Yes. Thank you for the question. So, indeed, this full version is more like an eye candy. So, if you want to make anything practical from it, then a bunch of filters usually the first step. And nowadays, I would say also unique analytics. So we have the graph, which stores the data, and then we have to call in the graph in a Python script and start to work out the different parts. We can do some of these things in a more visual way as well, but those tools are nowadays very limited. So the easiest part is to take the graph, not the nice visuals, but the raw data or the database, and go for it with Python.
Yes, please, Akos.
Yeah, just a very short addition to that, indeed, so this is like the first step when you have the infrastructure now to work on. And then comes network science or other data analytics when you reduce the complexity and you identify the nodes or the links which make the highest impact or have a central role or all of these. So this is to come, but we still lack this basic data infrastructure where we could use the analytics on. So this is the point, I think here. Yeah.
Just to say that it's very interesting.
Wait a moment, please, Eva.
Just a comment and thank you very much. It is a much nicer insight. I mean, way to reduce the information, right? Than text. It's much better and it's very good. Thank you.
Well, one image worth 1,000 words, right? So another way where we had this first flavor network, it was also a giant hairball at first, and they applied lots of statistical filtering to arrive at that very nice, clean structure. Maybe I won't find it right now, but there are ways, and then they had a visual output, but also that needed a unique, for instance, Python-based algorithm. So, it was here, no, the other one. Okay, never mind. So there were very clean structures and connections, but usually in practice there are loads and loads of weak connections. So first, we usually do some statistical filtering because it might happen that some of those connections are, well, their significance is beyond random, so we can trim the network. But also if we trim them, can we trim them because it's insignificant or the measurements were corrupted or not reliable enough? No, there are many, many questions there. And two questions here and there. Yes, there's.
Who wants to? Sorry.
So just one sort of imagining your largest figure is still very simple compared if you then start adding in dietary patterns and social built environment, all the other things related, all of which is my understanding of what these AI models are doing in their own black boxes. Have you worked applying this type of visualization to help us see the brains of some of these AI models also? Because you could imagine taking how ChatGPT answers a question, turning it into some simplified version where we could at least see something similar to this of how, like, it seems related to.
Not personally, but I've seen a group working on this, to trying to like reverse engineer how ChatGPT works to use that logic for their own projects. But so it exists, but we haven't done it here. Oh. Is it yours? Two or three? Yes.
Oh, please.
Yeah, okay. Just very quick question, okay. Yeah, you mentioned about the manual extraction of data and the curation. Do you think that some of the new technology can help you?
Well, it was actually Akash and his team who did that, so probably.
Yeah, just a quick answer. We want it to be systematic, and usually GPT or large language models and AI in many ways is not systematic. So we wanted to introduce this human systematic approach to the loop. But in fact, in the process, we use some machine learning to identify the relevant papers. For instance, there will be another talk today afternoon by Michael Sebek on how to use machine learning for identifying the relevant papers, and also there were a few tools used along the line, but still it was mainly human driven and validated. So, but that's another big question: how far human validation will go in the future? What will be done by machines? What by humans? By that time, we did it last year. it was still a lot of human work. Now, if we would repeat today, I think it would be more machines than last year. So it's evolving very quickly. Yeah.
We can discuss a little more. Yeah.
Thank you. Yeah, no, building on this prior discussion and linking, well, first I have to say very cool, very beautiful.
Thank you.
Thank you. But, building on this conversation, especially our colleague from TDU, is that right?
Yeah.
Yeah. So ontology, I think of as something profoundly human, right? So doctorate, Einstein physics, it's very clear to our human brain. Similar, our scientific approach would say you go from flavors through compounds to disease on the graph you showed. But is there not a way, is anyone working on not an ontological approach to creating a knowledge graph, but a mathematical one where the machine itself, we are teaching or training to find the correlations that don't match our pre-existing ontology? For Einstein doctor, there's probably enough data out there that it's easier, but maybe for disease and compounds, it's a little bit more difficult. But the approach of allowing the machine to figure out its own machine ontology, even if it's not relevant to us, and then coming back on a second pass and trying to interpret its ontological view of the world, non-human ontological view of the world. I hope my question makes sense.
Yes, it makes perfect sense. I'm not aware of work on this direction yet, but it makes perfect sense. So we would show, for instance, tremendous amount of data about what people eat and their health records, and just the two endpoints of the chain, and just let the machine figure out what's happening in between, right? Yeah, maybe we can revisit that question next year, given how quickly these tools develop. Yeah, one thing I was wondering here is exactly data security. What we also saw, I think, before that, whether we can use any cloud services or what GDPR allows us to do on having the detailed health records of people, connecting to what kind of food or diet they have. But thinking about that, I would bet that the legal background might be even more challenging than the technological, given where we are today. So that's my short maybe answer or potential answer. Yes, very good question indeed. Thank you.
Thank you very much.
Thank you.
Thank you for your questions. Thank you for a great presentation. And now, last but not least, I invite you to hear our next presenter, Paul Woolley from the Woolley Research. Could you put the presentation and Paul on the... Hi, Paul. I hope everything okay with you. Paul develops and promotes open science practices, fair data and evidence-based methods in toxicology and environmental health. 12 years of experience in systematic review has given him first-hand experience of the need to change how we report the methods and findings of research to make scientific data more accessible for computational processing. He is editor-in-chief of a new journal of evidence-based toxicologies, and we listen his talk about methods, ontologies, as underdeveloped tools in data readiness for AI. Paul, the floor is yours. Thank you very much.
Thank you very much. Right, I'm going to minimize this screen because it's a bit confusing. How long do I have, by the way? Because I'm aware it's 1/4 the hour now. So
you have 20 minutes, and after
20
some
minutes.
questions.
Lovely. Okay, good. Right, let's see how we can go. I'm just going to share my window here, so you should be able to see my presentation, I think. Let's just see if that's working. Is that working? Yes, fantastic. Okay, good. Right, so today I'm going to be telling a little bit about how the sausage is made in terms of ontology, I would say. So I'm involved in this new project, part of the GRADE working group, to develop a methods ontology to help with describing certainty of the evidence and the findings of systematic reviews and strength of recommendations for policy options when you're integrating evidence into decision making. Just trying to see if that's working. No, that's not working. Give me a second. That's working. Good. Right, so I've been introduced. I don't need to say much more. I'm just very interested in how systematic view, I think, has defined the data requirements and processes that we have in place for making sense of evidence, but it's also shown that human-based processes can't scale with the explosion we're seeing in publication of research and the number of decisions we need to make based on evidence. So we need to use artificial intelligence to help us make sense of scientific knowledge if we're to action it at any kind of scale, I would say. And I'm very much a process, not technology person. So this is definitely a presentation about how we are making ontologies. It is not a presentation about the technology by which we deploy them or make use of them, I would say. I have a lot of interests, which are just, excuse me, on this slide, so you can review this later at your leisure. And I want to acknowledge the contributions of Brian Olper, who's co-leading this project with me. He is the ontology expert. I'm more on the organisation end of things. Kevin Potty, Alonso Lorio, and Holger Schunemann for obviously initiating, encouraging this work. Joanne Dane-Bostel is our project coordinator, and we get nothing done without her cracking the whip. And the great working group is overwhelmingly positive response and support. And we've had over 60 contributors now, I think, to the development of this ontology. So obviously they deserve a lot of credit for the time they're putting in as well. So I was asked as part of this presentation to kind of try to connect AI data readiness with this work. So I think probably many of you are aware that ontology is the branch of philosophy concerned with what kind of things exist. I certainly am. I started as a philosopher. I have a master's in philosophy before I ended up in toxicology. I don't know how that happened. This concept was arguably repurposed in 1995 by computer scientists to describe any formal representation of a set of concepts within a domain and the relationships between those concepts. And ontologies are obviously very useful because it's difficult to know when people use different words for the same things and the same words for different things, if they're actually referring to the same thing at all. And flexibility of language in this way is very good, except science needs language to be very precise, because if we don't know what thing someone else is talking about or fail to successfully communicate what thing we're talking about, we can end up thinking we're talking about the same thing when actually talking about different things. Gene ontology was one of probably the first massive wide uptake ontologies where we've got agreed names for genes, because there are many. So we need to be very precise about when we're talking about which genes, we don't make any mistakes there. We see disease ontology widely used in health research, and we're seeing chemical ontologies come online for agreed names for chemical exposures. This is all in kind of the way for AI-ready data, because if humans have a system for understanding which thing they're actually talking about, this makes it much easier for a computer to correctly identify also which concept is being signified by the words that we are using to communicate with each other. What we're not seeing so much of yet, however, is methods ontologies, and that's what I want to talk about in this presentation. These are also potentially very useful because we can provide agreed terms and definitions for the processes that we use for creating and analyzing data. This will help people, I think, with complete and consistent description of the methods they use in their studies, so we know how they generated the data they did. That will make it easier for us to evaluate the quality and credibility of the results of those studies. And by making this information about methods more accessible to computers, the computers will be able to take on some of the work of study appraisal, which at the moment is done by humans, is largely subjective and based on quite incomplete understanding of the implications of a given methodological choice or potential bias in the findings of a study. And the bottom line here is that not many have been developed, and the grade ontology is probably one of the first. It's not the first. We're using the same protocol that something called SEVCO, which is a bias and statistics methodology, has been using. So in this talk, I'm going to try and convince you that methods ontologies are new but important. I'm going to give you a walkthrough of why we need methods ontologies and how to create them, and grade ontology is an example here. So I'll take you through the importance of data standards in research. I hope that won't be totally trivial to you all. I'm going to introduce you to grade itself as a de facto but informal data standard. Going to run through some specific benefits of grade as a methods ontology, talk a little bit about how the grade ontology is being developed. So that I'm a process person, I will go into the process. And then if I have time, which I might not, I will wrap up with some quite nerdy stuff about the layered infrastructure of research and how this relates to AI data readiness. But I suspect that might be beyond what we can do in the time we have. So first question, why do we need data standards in research? It's because, as I'm sure you're aware, we're under increasing pressure to make sense of complex evidence faster in response to more policy questions. We have an aging and therefore less healthy population, interacting with increasingly complicated environmental exposures. So modeling the impact of exposure on health is becoming more challenging, but more urgent. It's being exacerbated by climate change, so everything is happening much faster and we had answers yesterday. And scientists, to their credit, are doing a lot more research than they used to, but well, certainly publishing more data, but this gives us more evidence to make sense of, whilst the challenges of making sense of evidence are mounting. We're actually seeing 2,700 articles added to Medline per day as of 2022. Half of all research has probably been published since 2005, which I find a terrifying fact. And we've now hit 1 million articles per year in Medline, which I call the Dr. Evil threshold for publication. It's just basically too much. I know that you are food risk assessors, many of you, so you'll be very familiar with this chemical, bisphenol A, which really blew up in about 2012, 13 as one of like the poster child endocrine disruptors, widely used as a food contact material. There have now been 19,500 studies of bisphenol A, counting to the end of 2022. So that's 1,400 being published per year on this molecule alone. And that's just those indexed in PubMed. If we went to Scopus, we'd probably find a few more. And the problem with all of this research, and I think you'll know this because you're systematic reviewers and risk assessors, is that individual studies are often of unclear validity. Individual studies can be very hard to find, and data within studies is even harder to kind of get hold of. And it's just very difficult to reuse all this stuff. We're having to find needles in ever bigger haystacks. If we're doing systematic reviews, it can take 18 months to systematically review just 40 studies, and we're dealing with far more than 40 studies in a typical policy problem space, of course. So this is why a lot of people are increasingly focused on data standards. So we've got 3 types of data standards. So if we follow the Open Data Institute kind of framework for thinking about these things, we've got standards for guidance, excuse me, standards for terminology, and standards for data exchange. Standards for guidance, something I am a big fan of. So these are frameworks and recommendations for creating, collecting, analysing, and reporting data, which we hope improve one or more aspects of the consistency of how research is done and recorded, the validity and the transparency of science, and the sort of utility as well of scientific studies. So I think you all know about units and measures, codes of practice, standard operating procedures, and protocols of recording. So, you know, micrograms are an example of a standard for guidance. So how to describe how much something weighs. You'll probably all be familiar with GLP, so good laboratory practices for how to do research, so it has a certain degree of regulatory acceptability. And then those of you like me who have a lot of experience in systematic review will be very aware of the PRISMA framework for reporting systematic reviews, so how they're done, what they found. We also have standards for terminology, which I talked a little bit about already, but this is where we specify preferred terms and definitions for concepts used in a specific area or domain. Here what we're trying to do is provide a common language for people to use to express and communicate the information that they're presenting in their research. So here we use our controlled vocabularies and ontologies. So those of you who do medical research, or if we've got any GPs in the room, probably not, will be familiar with SNOMED, which is a disease ontology like WHO ICD-10. There is the gene ontology I mentioned already in Campbell, and then anyone who's done a PubMed search will be familiar with the medical subject heading as controlled vocabulary that helps you identify papers in PubMed by topic. Then we've got standards for exchanging data, which I won't dwell on, but is one of the most fascinating areas, I think, of data standards, because they're very intangible and difficult to understand. But basically what they are is a set of common formats and rules to support the interoperability and reusability of data. So if I've got data in my system that I've built for my purposes, but you think that that data has value to you, but you've got your system and you want to use my data in your system, then we need some way of moving the data from my system to your system without changing the meaning of that information or losing data in the process, as far as we're able to. So file formats be a classic exchange standard, data transfer protocols, data types. So those of you who use Microsoft Excel and then create a comma separated values file, that's a plain text way of demonstrating tabular data. That allows for good interoperability of that data between different systems. JPEG is an image compression format. Anyone who's used Uber or tried to plan a journey using Google Maps will have been inadvertently making use of the General Transit Fee Specification, which is a global standard for describing transport networks. And then those of you working in healthcare will know about the Fast Healthcare Interoperability resource, which is the international standard for sharing individual patient data between healthcare providers. So how does grade fit into all of that? So I don't know, if members, for a quick show of hands, who is already familiar with grade, and that'll help me just pitch this explanation. So put your hand up if you know what grade is. Okay, we've got a few people. Excellent. I think count of 3. So this is going to be tough because I've got to explain 2 things at once then. So what grade is basically a way of operationalizing our assessment of certainty in the evidence once we've done a systematic review. So when we do a systematic review, obviously we're trying to systematically gather all of the evidence that is relevant to answering a particular research question. And once we've analyzed the data and we've done a meta-analysis and we've got our bottom line results, so for example, we might find that exposure to air pollution increases number of cancers per 1,000 people by 3 people per 1,000 per unit of exposure or something. And then we'll be like, okay, good. So that's the estimate we have at the end of our systematic review. But we want to ask how credible that estimate is, because there'll be studies done in different ways to different standards that might not be directly on the thing that we're interested in, but relevant to the thing we're interested in, with different degrees of precision around the effect estimate. And this will have some impact on how certain we are that our results of increase of 3 cases of cancer per 1,000 people is true. So if the evidence looks like it is quite biased, that's going to reduce our certainty that our final estimate is true. If we're getting different results from similar studies with no explanation as to why that might be the case, that's probably going to make us less confident that our answer is true. If we've got very wide confidence intervals around our estimate effect size, that's going to make us less confident that our answer is true. And if we've got evidence of rampant publication bias as well, again, then we're going to be worried that maybe our answer isn't quite correct. So what grade does is it gives you a framework for systematically going through these domains, as we call them, of certainty that allow people working in different places at different times to use the same language and the same processes for evaluating certain evidence. So you've got a consistent approach between these different groups, and it's proved to be very useful. They also do something called evidence decision frameworks, which is the same kind of thing, but it concerns once you've got the evidence of health harm from your air pollution, and then you're thinking about, well, what policy options do we have for potentially implementing to mitigate this harm, that it gives you a way of evaluating the relative merits of the different policy options that may be available to decide how strong your recommendation should be for one policy over another. And that layers a set of additional factors, we call decision factors, on top of the systematic reviews that will be done into the health effects. So importance of the problem, the strength of evidence for desirable effects of the policy, the undesirable effects of the policy, the acceptability of the proposed policy, how feasible that policy is. And again, you can systematically work through these and you have a transparent way of showing to somebody else what it was you thought and how you got there. And then one person applying the strength of recommendations or ETD framework in one place, will produce a result that is interoperable with somebody doing that, using that same framework in a different place. And these have been cited probably about 300,000 times, I think, since they were first created in 2004, and they've been under continuous development since. So GRADE is basically a data standard because it gives you guidance on how to evaluate certainty in a claim to knowledge. So that's your certainty of evidence framework, and it gives you guidance on how to evaluate how desirable one intervention is over another. And it also provides a standard for terminology because GRADE has a set of preferred ways of talking about the concepts that are being used when you evaluate certainty of evidence and strength of recommendations. But there are a bunch of challenges for users, for sure, because it's a technical framework and terminology, which makes it challenging for users to implement consistently. So there's potential for mischaracterization of certainty and strength of recommendations when doing systematic reviews and developing guidelines. There's potential for misinterpretation of what certainty of evidence and strength of recommendations actually mean. And it can be very difficult to communicate shifts in meaning as well. So when one term is out of date and shouldn't be used, or when new terms are being added, alerting users of the GRADE frameworks can be quite challenging to achieve. So, for example, and I think this is one of the most illustrative, is that we have quite inconsistent understanding among different stakeholder groups or different people who use GRADE or come into contact with evidence of what it means, the difference between low and moderate certainty evidence. And I think particularly this misunderstanding drives some of the apprehension about use of epidemiological evidence by policymakers and some of the frustration that people who create epidemiological evidence have with how policymakers respond to their evidence, because low certainty sounds bad if you're a policymaker, but you can make decisions based on low certainty evidence, and inadequately communicating this is definitely a challenge in uptake of GRADE. There's some issues with inconsistent understanding of things like publication reporting bias. In GRADE, we're deprecating this term contextualized evidence because it's not helpful, but it continues to be used in the literature. And we've thoroughly deprecated quality of evidence as of about 12 or 13 years ago. And that's still being widely used when people should be using certainty of evidence instead. And again, it just impedes some understanding of the processes that are in place. So I'm going to skip through this bit because I am definitely running out of time here. So what we're looking to do is establish a centrally managed process and resource for tracking and communicating the complete set of GRADE-specific terms. And we're doing that by creating a machine-readable set of preferred terms, definitions for those terms, and then guidance supporting the consistent and correct application of those terms. So we have a full set of full description of the core concepts of the GRADE set of evidence and evidence decision frameworks. And to do that, we are following specified protocol, so protocol in the formal engineering sense, and it covers 7 important aspects of ontology relating to project team and governance, scope of the ontology, so 89 terms in this one, the methods for agreeing the preferred and alternative terms, definitions and guidance on use. Then we've got the process of approving those terms, publication promotion of the ontology, which is an understated aspect of the work, providing support, maintenance, development for the ontology. So in terms of project team and governance, the project is run by the GRADE project group. It's administered by Computable Publishing Limited, who provide the platform and the project management, and participation is voluntary by any self-nominated expert can participate in the project team that decides on preferred terms and definitions of those terms and then comments for application. So it's an open project. The project group meets on live calls once a week at the same time, so 3 p.m. on Fridays, to discuss a term, its definition, and its comment for application. When the group thinks the term is ready for vote, it goes out to an asynchronous vote. So again, anyone who's registered to be part of the project can vote as part of a balloting process as to whether or not the term they agree with the preferred term, the definition, the comment for application. If you vote against the term, saying it's not ready yet, you provide a comment to explain why, so we can use that information in the next synchronous discussion meeting. If you have unanimous approval and require unanimous, then the term is accepted. If there isn't unanimous approval, the term is discussed on the next live call, and the term and definition, whatever parts need to be revised are revised, and then it's put back out to vote again for reballoting. And this process iterates until unanimity. We're publishing and promoting and supporting the ontology through a grade concept paper, which we're currently finalising. When we've completed version 1 of the ontology, we'll publish grade guidance. These tend to be highly cited and a good way of getting information out about the availability of the ontology. There's acceptance via the standard grade process, which is quite a rigorous voting and approval process that happens at a level above the ontology, and then final acceptance by the grade guidance group. We then plan on a bunch of promotional articles to raise awareness of version 1 as well. And we're going to proactively identify systems that may implement the grade ontology to offer support for implementation, monitor its use, and generate change requests so we can improve the ontology. Yeah, and then we've got a change request approval process. And so far, as of at least 3rd of September, which is the time we last did the data on this, had 58 participants from 22 countries involved in term development and voting, 14 terms approved via 65 ballots. So we get a lot of ballots per term, between 1 and 11 ballots to approve a term, average of 53 votes per term in the ontology. The most difficult one has been defining imprecision, so the degree of variation or spread among probable values for the estimate effect. We had to go around 11 times to get that sorted out. That was quite tough work. Publication bias required 8 ballots. That was also a pretty tough one. So systematic differences between the study results that are available and the study results that are not available. I've got some examples of terms here, but again, slightly running out of time. But for example, we define certainty of evidence, which is probably the core central concept of the grade certainty of evidence framework. So that's confidence, the true value of the measure being estimated lies on one side of a specified value or within a specified range. And that was the first term we approved. We've got risk of bias approved, as said, and inconsistency approved as well as another example. So that's variations in the findings from which the estimate of effect was derived. This is quite tight work. It's very transparent, so you can see in the term display interface here, this is just how we're doing it in our system. All of this stuff is machine coded, so it can be displayed how anybody wants in another system through like a JSON format, where we have machine readable representations of the term. We've got the preferred term shown, the definition shown, and we also make it transparent by showing who the term definition editors are. And also down at the bottom there, you can see the documentation of expert group agreement. So we actually show how many rounds of voting the term has gone through, who did the voting, and what the results of the votes were. So you can audit all of our work essentially. I think so to conclude that this is slow, challenging work, and then some. Like we've been cracking away at this for 6 months, and we're about probably halfway through, I think. It is extremely valuable to bring in through this public participation process, which I think grade are a little bit nervous about originally, but what it's shown is by bringing in people who are not grade specialists into the process, that it actually challenges us as experts in grade to communicate what we're doing to an audience that would have a lower level of familiarity with these terms, and it does make the definitions much better. Our rigorous protocol is critical. And in fact, one of the major challenges here is you need a high level of simultaneous expertise, both in the topic that we're developing terms for, but also in moderation of what are effectively focus groups. And it does seem to work, but I'm not personally sure if it's how scalable this is, because if you went through this process for every term that you needed to use in research, I don't know if you'd ever get finished. So some people have started suggesting folksonomy approaches instead, and that's something that I think I'm personally going to be looking into in future. So I've definitely run out of time here. I'm already over time, so I'm afraid I'm not going to get to talk to you about my favorite thing, which is the layered infrastructure of research. I'm just going to say thank you very much for listening. If you're interested in joining the project group, you can zap that QR code on the bottom right. If you're interested in having more discussion with people like me, you can join the evidence-based toxicology collaboration and join our open science working group, which is probably one of my favorite roles at the moment. We're working at the moment on developing semantic authoring tools for researchers to use as our joint project. Thank you for your attention and time. And I guess, is there any time for questions?
Yes.
Hope there's time for a couple.
Yes, thank you very much, Paul, for your great presentation. It's open to the audience. Please, Paul Devalier from EFSA.
Thank you. How do you reopen the definition of a term? Can that be done?
Yeah, so someone can just issue a change request, and then that will be evaluated by the group, and then we reopen the term. So someone would basically give the reason why the term needs reopening. We're actually going to be reopening 2 terms already because the grade working group is also developing its grade or revising its grade handbook. And there's good reason for thinking that we should change the risk of bias term to study limitations and change the publication bias term to dissemination bias to address some of the ambiguities and what publication actually means as a concept.
Okay, next question.
Hi, boss. Thank you for the inciting presentation. I have, I like your approach of this focusomy or something like that you told. But I'm also trying to lead some of this ontology development work, and I was wondering where we should go with the fork, which democracy can be messy, or we go with the controlled democracy, where we have the selected group of experts who first define the term and then open for the other people, the larger community, to comment on that. So what should be the best approach to go for that? Yeah.
So we think our approach is quite good, actually. So we don't worry about, we resolve the issue of expert discussion and lay involvement just by allowing both in the asynchronous discussion, allowing both in the synchronous discussion, so the weekly meetings, and we just manage that through good facilitation, I think. And that way you get the input of people like, well, I don't really understand what that means. And you can either fill in some of the theory, so you kind of you go through that educational process that somebody might need if they're not like an expert in the term, but also by them not understanding as an expert, you're forced to question whether or not you're communicating what you're doing clearly or not. And then through the asynchronous voting, because you can't vote no without providing a comment. So that comment then goes back into the synchronous discussion. And then I think that kind of gets away from the expert versus lay kind of sense that those are separate things or kind of dichotomy, and you just handle both at once. So it is very democratic. And then because we require unanimity before a term is approved, then we set a very high standard for consensus as well. So we do have some backstop plans, like if we can't get consensus, but so far we've not had to implement that. We've always been able to get a consensus, and we just patiently keep revising until we hit it.
Any other question? Well, Paul, I would like to ask you, what are, in your view, what are the ethical implications with the using of ontologies and semantics in these AI systems?
The ethical implication, I'm not quite sure, because using terms correctly seems to resolve, or it helps address some of the issues with, I guess, AIs using terms incorrectly, right? So I think it has the potential for reducing error through misunderstanding of terms. Like, you can tell the machine what the concept means through these kind of ontology development processes, rather than the machine having to figure out through, however sophisticated statistical modeling, what it thinks the term means. So it reduces the potential for error, particularly in areas maybe where training sets are going to be limited, concepts can be quite ambiguous or inconsistently used. I think it probably has some advantages there. I don't know if any of those are ethical specifically. I think they're just quite practical. They're just quite expensive to build. Like, it takes, a meeting once a week for 18 months probably to do the first version of the grade ontology, and we're 5 months, 6 months in. A lot of person hours.
Thank you very much. It was a great session. I don't know if anyone has a last question. It was great. I would invite you to applaud our presenters, our great presenters. And Paul, to you, thank you very much. And for all, we invite you to go to the lunchtime and to make the network flowing better and better. Paul, thank you very much, and I hope see you soon.
Yes, thank you. I'm sorry I couldn't make it in person. I really would like to have been there. It sounds a really interesting meeting. So.
Thank you.